So, number one, 5 major areas of specialization in earth science. That's what we're looking for first. So, scope of earth science. So, from the maps you use when traveling to the weather reports you use when deciding whether or not to carry an umbrella, earth science is a part of your everyday life. The scope of earth science is vast. It is partly for this reason that the broad field of earth science is often broken into 5 major areas of specialization. So, astronomy, meteorology, geology, oceanography, and environmental science. So, those are your 5 major branches. So, that answer is number one, right? 5 major areas of specialization. We got those right here: astronomy, meteorology, geology, oceanography, and environmental science. Now, our next question: what is astronomy? Well, astronomy, the study of objects beyond Earth's atmosphere, is called astronomy. So there's your definition. You really don't necessarily need is called astronomy. So if you don't want to have all of that there, you could, sort of redo that and just say the study of objects beyond Earth's atmosphere. So we'll call that astronomy. Okay. Prior to the invention of sophisticated instruments such as the telescope shown in Figure 1, just down here. Okay. Many astronomers merely describe the locations of objects in space in relation to each other. Today, Earth scientists study the universe and everything in it, including galaxies, stars, planets, moons, and other bodies they have identified. Astronomers focus on the movement, composition, and structure of bodies in space. And we do this with telescopes. We do this with land-based telescopes, space-based telescopes. We send out probes. We send out rovers, robots and stuff that are collecting samples like on Mars and stuff. So we have all these different ways that we study this now. All right, next question, number 3. What is meteorology? So meteorology is the study of forces and processes that cause the atmosphere to change and produce weather. That is meteorology. Meteorologists also try to forecast the weather and learn how changes in weather over time might affect Earth's climate. They use technology ranging from satellites to thermometers to make forecasts and to analyze trends. Okay, so that is our definition of meteorology. Later on, we'll do more stuff on climatology. I don't do a whole lot on just meteorology, though. All right, but that's number 3. Number 4, what is geology? So geology, the study of materials that make up Earth, the processes that form and change these materials, and the history of the planet and its life forms since its origin. That is the branch of earth science known as geology. Geo, earth, ology, study of. So, geologists identify rocks and fossils, study glacial movements, interpret clues to the Earth's 4.6 billion year history, and determine how forces change our planet. So, in short, that is geology. There's a whole bunch of stuff we'll do on geology later. So. Number 5, what is oceanography? And I've heard that word pronounced a few different ways lately, but oceanography is how we pronounce that. The study of Earth's oceans, which cover nearly 3/4 of the planet, is called oceanography. Pretty simple. It's the study of Earth's oceans. Oceanographers study the creatures that inhabit salt water. That's marine biology. They measure different physical and chemical properties of the ocean water. And observe various processes in these bodies of water. When oceanographers are conducting field research, they often have to dive into the ocean to gather data as shown in Figure 2. So you may be diving with scuba gear, maybe diving in submersibles like submarines, stuff like that. So there's different ways we end up having to dive down to get this information. Sometimes it's done with remote sensing too, like things like sonar or using little remote control vehicles that have cameras on them and stuff like that too. So, all right, but that's oceanography, study of Earth's oceans. Okay. Oops. Then what is environmental science? So environmental science is kind of like the baby of these. All these others are much older. Environmental science is only about maybe 100 years old, something like that. The study of interactions among organisms and their surroundings is called environmental science. More specifically, that is more of a definition of what we call ecology in biology. is the study of organisms and their surroundings. Really, environmental science includes human influences on that, human factors. the activities of humans. How do we affect this stuff? But environmental scientists study how organisms impact the environment both positively and negatively. The topics an environmental scientist might study include the use of natural resources, the effects of pollution, alternative energy sources, and the impact of humans on the atmosphere. Okay, so again, we have this humans on the atmosphere, pollution. There are natural sources of pollution, but largely looking at man-made pollution. Alternative energy sources. Again, that's more of a human-based thing. So, anyway, environmental science largely looks at the influence or impacts of humans on natural systems. And then subspecialties. So the study of our planet is a broad endeavor, and as such, each of the 5 major areas of Earth science consists of a variety of subspecialties. These include climatology, paleontology, and environmental chemistry. The descriptions of several subspecialties of Earth science are listed in Table 1. This is a good point, a good time to note that just because it's not highlighted and it's not a question on the study guide, that doesn't mean that it's not going to be on a test. You may see something about subspecialties when we get around to test time. Okay, you all right? Good. But you may see something about subspecialties when we get around to test time. So don't totally ignore it because there's not a question about it, all right? But astronomy, some of the subspecialties, astrophysics, looks at the physics of the universe, including the physical properties of objects in space, looking at orbits, orbital periods, that sort of thing. Planetary science looks at planets in the solar system and the processes that form them. Also looks at exoplanets, which are planets outside our solar system. We know about a lot of those now. So that's some of our subspecialties for astronomy. For meteorology, you've got climatology as a subspecialty. Looks at patterns of weather over long periods of time. Atmospheric chemistry looks at the chemistry of Earth's atmosphere and the atmospheres of other planets. So looking at the chemistry of those, so the gases that surround the planets. Geology, you got paleontology, which looks at the remains of organisms that once lived on Earth, looks at ancient environments, etc. So these are like your dinosaur hunters, your fossil hunters, etc. Geochemistry looks at Earth's composition and the processes that change it. And then oceanography looks at, you have physical oceanography, which looks at the physical characteristics of oceans, such as salinity, waves, currents, etc. You have marine geology, which looks at geologic features of the ocean floor, plate tectonics of the ocean, etc. We said marine biology a minute ago, which refers to or studies like all the organisms, all the animals and stuff living in the oceans. Then environmental science, you have environmental soil science, which looks at interactions between humans and the soil, such as the impact of farming practices, effects of pollution on soil, plants, and groundwater, etc. You have environmental chemistry, which looks at chemical alterations to the environment through pollution and natural means, etc. So those are some of your subspecialties. There are others out there, but that's some of them. All right, so importance of earth science. I want to fix this because I have this in the wrong order. There we go. Okay, so importance of earth science. So the study of science, including earth science, has led to many discoveries that have been applied to address society's needs and problems. The application of scientific discoveries is called technology. Technology is transferable, which means it can be applied to new situations. So that gives you an answer then for number 7. What is technology? Well, technology is the application of scientific discoveries that is transferable from one situation to another. Okay. Science is different in that science is basically a process of gaining knowledge, of learning new things, without worrying about how you're going to use it or does it have any practical purpose or anything like that. A lot of scientific discoveries have zero practical applications. Once you make a practical application for it, though, then we call that technology. Okay. And then the next question, give 4 examples of products that were a result of the space program. So freeze-dried food, ski goggles, laptops, ultralight materials, etc., used to make pieces of sports equipment. These were all created from technologies used in the space program. Smoke detectors were also invented as part of the space program and were adapted for use in everyday life. Okay, so you could take, there's like 5 examples right there, pick 4 of those, and that would answer number 8. Okay. Number 9, give 4 examples of how earth science impacts society. Okay, so this one gets a little trickier. There's like 3 big ones here, and then each one's kind of divided up into some smaller chunks. But in addition to making life easier, technology can make life safer. For example, earth scientists monitor and analyze natural disasters ranging from earthquakes to hurricanes. So that's kind of one impact on society. So we monitor and analyze natural disasters. So they help predict when these disasters will occur. So you could use that as an example. But this allows people to seek shelter and evacuate an area. Earth scientists also aid in the aftermath of a disaster, mapping areas affected by natural disasters with satellite and aerial images. Helps relief workers gain safe access. Okay, so mapping these areas is also helpful. All right, then. But anyway, so mapping these areas helps relief workers gain safe access. Relief workers are better able to prepare for the challenges. We're looking at changes in local geography because bridges can be washed out, etc., destruction of buildings, other physical challenges in the disaster zone. So having aerial images and satellite data and stuff can tell you more about what's going on in an area before you get there. So really get 2 or 3 things from that if you wanted to get those 4. Earth scientists also work to improve farming methods. Okay, I want to change the color of this so it matches the other ones. All these green ones are part of this, this answer. Helping to produce more food for a growing human population. That is one effect of earth scientists, so working on farming practices. Precision farming provides farmers with detailed data about soil composition, topography, and pest infestations. The data gathered by satellites and computer simulations allow farmers to increase crop yields, reduce waste, and protect natural resources. So you could use that as an example, just saying improving farming methods, collecting data about soil composition, so moisture, soil nutrients, etc. All of that could be part of your answer for that. I need to change the color for that one too. In addition to an adequate food supply, people need clean water and clean air. So earth scientists, such as those in Figure 3, monitor air quality and water quality and develop strategies to reduce environmental degradation. So they're doing water testing here, water sample testing, or water quality testing. Through computer simulations and other studies, important discoveries have been made or are being made about how Earth systems are modified in response to human activities. So again, monitoring water quality, air quality, etc. So you can kind of piece together 4 examples from that. Really got 3 big examples there. Okay, so that's number 9. So kind of a long answer for that one. Number 10, how has the study of earth science changed our worldview? So ancient people had a very limited view of their surroundings. Okay, so you kind of start with that. So ancient people had a very limited view of their surroundings. They were not sure of the shape of the earth or its land masses, and then through exploration and advances in mapping technology, we now have a clear image of Earth and can navigate around the world. We also know a lot about the universe around us and discovering planets, other planets outside the solar system, et cetera, et cetera. There's all kinds of things that we've discovered there. So we now have a much better idea of the Earth, how it works, its history, how other planets work, how the universe works, et cetera, through Earth science. So we went from this very limited worldview to having a much better understanding of how things work. But Figure 4 shows some advances in earth science over time. All right. So anyway, so number 10 is kind of these 2 here. Number 11, 2 major events in earth science since 1900. Well, I could pick 2 of these down here. Okay, so these are major discoveries since 1900. So 1907, scientists began using radioactive decay to determine that the Earth is billions of years old, not just thousands of years old. This method will be used to develop the first accurate geologic timescales. 1913, French physicists discovered the ozone layer in Earth's upper atmosphere and proposed that it protects Earth from the sun's ultraviolet radiation. 1925, Cecilia Payne's analysis of the spectra of stars reveals that hydrogen and helium are the most abundant elements in the universe because they are the most abundant elements in stars, and there are a lot of stars. 1936, Inga Lehman proposes that Earth's center consists of a solid inner core and a liquid outer core based on her studies of seismic waves. That's how we kind of have an idea of what the structure of the Earth looks like. She studied earthquake waves, seismic waves, and kind of used them almost like an ultrasound. Like, how do we know what a baby looks like before the baby's born? You bounce sound waves off of it, and you build up an image from that. She kind of built up an image of what the interior of the Earth looked like by collecting data from a bunch of different seismic stations around the planet. You know where the earthquake happens, you know what different seismic stations pick up from that earthquake, and you can kind of start piecing together almost like an ultrasound picture of the interior of the Earth. 1962, Harry Hess's seafloor spreading hypothesis, along with discoveries made about the ocean floor, lays the foundation for plate tectonic theory. 1990, the Hubble Space Telescope goes into orbit, exploring Earth's solar system, measuring the expansion of the universe, and providing evidence of black holes. 2004, sediment core retrieved from the ocean floor discloses 55 million years of Earth's atmospheric and climate history. The sample reveals that the North Pole once had a warmer climate. 2015, scientists observed gravitational waves for the first time. The existence of gravitational waves was predicted by Einstein in 1916. And then, like 2021 or 22, I think it was 21, might have been 2020. Actually, I think it was 2020. Anyway, the Webb Space Telescope, infrared telescope, basically went into orbit and has basically been giving us better information than the Hubble telescope really ever gave us. So we're getting a lot more information now from that. Anyway, so Earth systems. So scientists who study Earth have identified 4 main Earth systems. You have the geosphere, the atmosphere, the hydrosphere, and the biosphere. That is your answer for number 12. Okay. Number 12, you have 4 main systems. You have the geosphere, the atmosphere, the hydrosphere, and the biosphere. Each system is unique, yet each interacts with the others. When investigating Earth systems, scientists define the boundaries of each system. In fact, in science, that is what a system is. A system is something you can draw a boundary around and study it. But the inputs and outputs of these systems can be analyzed using different models. Okay, so that again is your answer for number 12. Number 13, what is the geosphere? Well, the geosphere is the area from the surface of the Earth down to its center. It's all the rocky part below our feet. This is called the geosphere. The geosphere is divided into 3 main parts. You have the crust, the mantle, and the core, and these parts are illustrated in Figure 5. So number 14 says name and describe the 3 major parts of the geosphere. So you have the crust, the mantle, and the core. It says to describe them. You kind of list where they are, maybe. Like the crust is on the outside. It's like 8 to 40 kilometers thick. I'll probably get most of my description from this, really. The mantle is below the crust, and it's about 2,900 kilometers thick. The outer core is about 2,250 kilometers thick below the mantle, and then the inner core is at the very center of the Earth. It's about 1,300 kilometers in diameter. You get more of that from here. So the rigid outer shell of the Earth is called the crust. It's kind of a description of it. There are 2 kinds of crust. You have continental crust and oceanic crust. Continental crust can be billions of years old. It's generally older than oceanic crust, which is less than 200 million years old. Just below the crust is the mantle, so that's part of your description of those. The mantle differs from the crust both in composition and behavior. The mantle ranges in temperature from 100 degrees Celsius to 4,000 degrees Celsius, much warmer than the temperatures found in the crust. And then below the mantle is Earth's core, where temperatures reach as high as 7,000 degrees Celsius. So again, to kind of answer this as far as name, the name should be pretty simple. You got the crust, the mantle, and the core. Those are the three major parts of the geosphere. To describe them, you could do a few different things. You could talk about the structure, like the rigid outer shell is the crust, below the crust is the mantle, and it has a different composition and behavior from the crust. And then below that, you have the core, or you can come back up here and talk about like the thicknesses of those. Still kind of want the order of those: crust, mantle, core. They kind of go in that order. Also, number 15, compare the age of continental and oceanic crust. Well, that's right here. So there are two kinds of crust. You have continental crust and oceanic crust. Continental crust can be billions of years old. It's generally older than oceanic crust, which is less than 200 million years old. So that kind of gives you a comparison of the ages of the crusts. All right. Then number 16, what is the atmosphere? Well, atmosphere, the blanket of gases that surrounds a planet, is called the atmosphere. Earth's atmosphere contains about 78% nitrogen, 21% oxygen. The remaining 1% of gases in the atmosphere include water vapor, argon, carbon dioxide, and other trace gases. Earth's atmosphere provides oxygen for living things, protects Earth's inhabitants from harmful radiation from the sun, and helps to keep the planet at a temperature suitable for life. So that answers a few questions. So first off, what is the atmosphere? You have a definition right there. Blanket of gases surrounding our planet or any other planet or any other moon or whatever. It's the gases that surround a body in space. What is the composition of the atmosphere? Composition means what's it made of. So if you talk about the composition of something, what is it made of? Okay. In this case, 78% nitrogen, 21% oxygen. Yes, you want the percentages, because a lot of people think the atmosphere is all oxygen. We think, oh, we're just surrounded by oxygen. Like 21% of the air surrounding you is oxygen. 78% is nitrogen. Most of what you're breathing right now is nitrogen gas. Okay. And then the remaining 1% includes things like water vapor, argon, carbon dioxide gas, and other trace gases, like neon and possibly hydrogen gas and helium gas and things like that. Those could be out there. Natural gas, like methane, is also in the atmosphere. But that is our composition of the atmosphere. What's it made of, and what kind of ratios, what kind of percentages are you talking about for each of those things? And then number 18, describe 3 ways the atmosphere helps support life on Earth. Well, that's this part here. Provides oxygen for living things, protects inhabitants from harmful radiation, and then also keeps the planet at a nice temperature for life. Okay, so that's sort of 18 right there, I think. Yeah, 18. Number 19, what is the hydrosphere? Well, all the water on Earth, including the water in the atmosphere, makes up the hydrosphere. So there's your answer for that one. So what is the hydrosphere? Number 19, sorry. What is the hydrosphere? All the water on Earth. Composition of the hydrosphere is about 97% of Earth's water exists as salt water, while the remaining 3% is fresh water contained in lakes and rivers, beneath Earth's surface as groundwater, and in glaciers. Okay. So that is number 20, composition of the hydrosphere. Okay. And then what is the cryosphere? So number 21, well, that's down here. The region of permanently frozen water on Earth is called the cryosphere. Cryosphere happens to be shrinking. You've got glaciers melting, et cetera, et cetera. But then only a fraction of Earth's total amount of fresh water is in lakes, ponds, streams, and rivers. A lot of our fresh water is actually tied up in glaciers, which are melting and going into the ocean and becoming part of the salt water. So, all right, next, biosphere. What is the biosphere? Number 22. Coming on down here. So the biosphere includes all organisms on Earth and the environments in which they live. So that is your definition for the biosphere. Most organisms do live within a few meters of Earth's surface, either above or below, or on. But some exist deep within the vast ocean, deep underground, high atop mountains, actually in the atmosphere, on grains of dust, things like that. You have bacteria. So there's life in a lot of places you wouldn't expect. Now, as illustrated in Figure 6, Earth systems are dynamic and interactive. Feedbacks between the biosphere and other Earth systems cause a continual coevolution of Earth's surface and living things. In other words, living things change the Earth's surface, but then the Earth's surface and atmosphere and stuff change living things. So you have a warmer atmosphere, things are going to evolve that live in that warmer atmosphere, etc. But for example, the atmosphere of early Earth did not contain oxygen roughly 2.5 billion years ago. Photosynthesizing organisms in Earth's biosphere helped form Earth's present atmosphere by releasing oxygen as a byproduct of photosynthesis. The addition of oxygen to the atmosphere greatly influenced the evolution of complex life forms. So before that oxygen, everything was like single-celled organisms. So, the last question we have here, what is a feedback effect or what is a feedback loop? Well, some interactions among Earth's systems cause feedback effects that can increase or decrease the original changes. So in other words, it's a feedback effect is an effect where that's great. That's in the recording now. But a feedback effect is something where you have one thing happen and that causes the original change, whatever that was, to increase or decrease. Like, for example, well, the example here.
That bell is the indicator that half-day students are dismissed for lunch. This is your last announcement. You will now listen for the bell. At 10:45, there will be a bell. That bell is to dismiss the half-day students riding the bus to go to lunch. Thank you.
Okay. Anyway, as an example of a feedback effect, when trees in the biosphere are cut down, rates of photosynthesis decrease because there are less trees, and that affects the atmosphere because photosynthesis decreases. That means CO2 levels can rise, O2 levels may fall because of that change in photosynthesis. Another example is melting ice, like melting glaciers. Ice is reflective, reflects a lot of heat and light back into space. As it warms up and those melt, they expose dark soil, dark rocks, dark water underneath them, which absorbs more heat, which causes more warming, which causes more melting, which causes more dark surfaces to be exposed, which causes more heat to be absorbed and released, which causes more melting, etc. That's a feedback loop. Another example of a feedback loop, anybody ever stick a microphone in front of a PA system or a guitar in front of an amp or anything like that? And whee, that noise? Okay, that's feedback. That's a positive feedback loop. Yeah, that is a positive feedback loop. You have the sound being picked up by the microphone, fed through the amplifiers, amplified coming out the speakers, that sound gets picked up again by the microphone, re-amplified, and it keeps going. Life's better with sound effects. All right.